Hello, my name is Georgina Campany and I'm going to summarize the main results of my PhD work that aim to perform frequency differentiation of healthy and pathological lung tissue through minimally invasive electrical impedance spectroscopy. Let me start by introducing you the problem statement of my work related to lung diseases. 5 of the 30 causes of death worldwide are due to a lung disease. Of these, lung neoplasm is one of the most lethal types of neoplasms, causing 1.6 million deaths annually. The diagnosis of lung disease is performed with a first acquisition of a radiological image, followed by the pathological lung tissue sampling with procedures such as biopsies and bronchoalveolar lavages. When lesions are located in the central tree, the sampling is relatively easy. However, in peripheral lung lesions, the sampling is more complicated. This is an example of how the sampling is performed through a bronchoscopy. As we can see, with central lesions, there are visible tissue changes due to the pathology. However, in peripheral lung lesions, there are no apparent changes. A correct lung sampling is crucial for the correct diagnosis of lung diseases. For this reason, it is extremely important to apply new techniques for diagnosis to complement the actual ones. The study aimed to apply bioimpedance measurements to differentiate between lung tissue states. The bioimpedance is defined as the capacity of the tissue to oppose when an electric current is applied. It depends on the frequency and is described with complex numbers, with a pure resistive element due to the conductivity of the intra- and extracellular medium and a capacitive reactance that describes the capacitive behavior of the cell membranes. This capacitive reactance is described with the equation in the screen. As we can see, it is inversely proportional to frequency. For this reason, the bioimpedance is higher at low frequencies and lower at high frequencies. The bioimpedance measurements were obtained with a bronchoscope, following a bronchoscopic process. The measurement system consists of 3 devices: an insulated front end, a rack PC platform, and an analog optical interface front end to connect the PXI with the insulated front end. The system includes an arbitrary waveform generator that generates a multi-site excitation signal, which is a broadband signal composed of 26 frequencies between 1 kHz and 1 MHz. The objective of the study is to differentiate between healthy and pathological tissue from patients with different respiratory diseases: neoplasia, fibrosis, pneumonia, and emphysema. To differentiate between lung tissues, the most discriminative frequencies were 15 and 307 kHz. With the box plot, we can see that the impedance modulus and resistance is higher as higher is the air content in that tissue, such as emphysema, characterized by a tissue destruction. On the contrary, we can see that phase angle and reactance is higher as lower is that air content, as for example in the neoplasms, characterized by an uncontrolled cell growth. The statistical results of one-way ANOVA and Kruskal-Wallis show statistical significance in all the variables analyzed. However, post-hoc tests show significance between all pairs of tissues, except between neoplasms and fibrosis and pneumonia, and between healthy lung tissue and emphysema. Linear discriminant analysis results also show higher variability in the data, as higher is the proportion of air tissue, such as in the case of emphysema, which is the tissue with higher variability. Moreover, linear discriminant analysis is in conjunction with the statistical test of ANOVA and Kruskal-Wallis and the respective box plots. It shows little separation between pairs of tissues that were not different in terms of statistical significance. As conclusion, we can say that the variability due to the increase of air content in emphysema leads to the no differentiation between emphysema and healthy lung tissue. The increase in reactance values in neoplasia and fibrosis denotes the increase in the density of cells present in this tissue. The similarity between neoplasia and fibrosis in terms of the increase in tissue and cell concentration does not allow differentiation between both pathologies using minimal invasive bioimpedance measurements. Finally, regarding the no differentiation between fibrosis and pneumonia, the characteristic of lung condensation makes it difficult to differentiate between both pathologies. The final conclusion is that the greatest contribution is the ability to differentiate between those pathologies that lead to an increase in tissue and inflammatory cells and those that contain more air and destruction of alveolar septum. Thank you.